PowerPoint presentation. In this, we are going to talk about the basic postulates and general principles of quantum mechanics. These principles forms the basis of this quantum theory. Postulate 1 is about the state vector or wave function related to any physical system. Now, the state of a system is completely specified by its wave function. In classical mechanics, the motion of a particle or a system is completely described by Newton's equations. Newton's equations and the forces involved enable us to predict the future behavior of the system. Such predictions are not possible in quantum mechanics because the uncertainty principle states that the position and momentum of the particle cannot be determined simultaneously to any desired precision. The uncertainty principle has no practical importance for macroscopic bodies. For small bodies like electrons, atoms and molecules, they obey uncertainty principle and cannot be neglected. This leads to first postulate of quantum mechanics. The state of a quantum mechanical system is completely specified by a function psi of x that depends upon the coordinates of the particle. This function is known as the wave function, and it cannot be measured directly because it is a fixed quantity, but the square of the modulus of the function, that is modulus square of psi of x, is proportional to the probability of finding the particle at a particular point or in a particular location. The total probability of finding the particle somewhere in space must be unity, because a particle must exist somewhere in space at any time. And also, the finiteness of this integral implies that mod psi squared vanishes at infinity, and hence psi must tend to 0 as x tends to infinity. The probability interpretation of the wave function makes it necessary that it should satisfy certain conditions known as admissibility conditions. There are three conditions, that is, the wave function should be finite everywhere and it should be single valued. Also, the wave function and its first derivatives must be continuous functions of x for all values of x. And it can also be proved that the probability is conserved, that is, rate of change of probability with respect to time will be equal to 0. So the postulate 2 describes the operator formalism of quantum mechanics. Any dynamical variable can be related to an operator, and especially linear operators. So, to any observable in classical mechanics, there corresponds a linear operator in quantum mechanics. The table given here shows some observables and the corresponding operators. For example, the position of a system is described by the symbol x and operator x, and the operation is just multiplication by x. In 3 dimension, it is r. The momentum operator p is represented by minus IH cross del in 3 dimension and minus IH cross dou by dou x in 1 dimension. Now, in right, some more observables and the corresponding operators are given. The kinetic energy is represented by the operator K, and the operation is minus h cross squared by 2m into del square. The potential energy is V of x, and the operation is multiplication by V of x. The total energy is represented by the Hamiltonian operator H, and the operation is minus h cross by 2m into del square plus V. The angular momentum is represented by the operators Lx, Ly and Lz, the components of angular momentum I mean, and Lx is represented by the operator Ypz minus Zpy, following the definition, that is L is equal to R cross P. Ly is equal to Zpx minus Xpz. Lz is equal to Xpy minus Ypx. Linearity of the operators. An operator is said to be linear if it satisfies the equation given here. A, the operator operating on the linear combination of two functions f1 and f2 will be equal to linear combination of the result of the operator operating on f1 and the operator operating on f2 individually. And we have to define the eigenfunctions and eigenvalues of an operator. So if the operator A satisfies this equation, A phi is equal to small a phi, this equation is known as the eigenvalue equation, and the function phi is known as the eigenfunction of the operator A, which belongs to the eigenvalue small a. The eigenvalue A is said to be degenerate if more than one eigenfunction belongs to A. Here, the meaning of eigenfunction is if the system is in one of these states represented by phi, then it will have the value A. The postulate 3 tells about the eigenvalues. That is, it states that in any measurement of the observable associated with operator A, the only values that will ever be observed are the eigenvalues which satisfies the eigenvalue equation. That is, if you measure the particular quantity by doing an experiment, then the results of the experiments will be the eigenvalues. As a specific example, consider the measurement of energy. The corresponding operator is Hamiltonian operator, and the eigenvalue equation is H psi is equal to E psi. Here E or the energy eigenvalues. Postulate 4 deals with the expectation value of an observable. That is, according to postulate 1, wave functions have a probabilistic interpretation. Hence, we can use them to calculate the average value of physical quantities. For example, the average position of a particle in a given space is given by expectation value of x is equal to integral psi star x psi d. It means that the system or the particle is in a particular eigenstate psi, then the expectation value or the average value of the position is defined by this integral. This leads to the fourth postulate. If a system is in a state described by a normalized wave function psi, then the average value of the observable corresponding to the operator A is given by this integral. Postulate 5. The postulate 5 talks about the time dependence of wave functions. That is, the wave function or state function of a system evolves in time according to the time dependent Schrodinger's equation psi is equal to I h cross dou psi by dou t. Then we will talk about an important and interesting quantity called wave packet. The superposition of harmonic waves can be represented like this. It is sum of the harmonic waves. They are represented by this integral. This integral represents a wave packet. For any general system, the Schrodinger's equation contains the imaginary quantity I. This sets this apart from the partial differential equations of classical physics. Therefore, the wave function must be a complex function of x and t. For a free particle moving in three-dimensional format given here, that is I h cross dou psi by dou t is equal to minus h cross squared by 2m del square psi. Here, the operators involved in this Schrodinger's equation, that is dou by dou t or del square or linear operators. Therefore, this eigenvalue equation will obey the superposition principle. That is, if you take psi as the solution of this equation, psi 1 and psi 2 are two different solutions of this equation, then their linear combination will also be a solution of this equation. So this will lead to an important concept that if a particular if two harmonic waves are solutions of this equation, then their linear combination will also be a solution, or we can say that Schrodinger's equation has a wave packet solution. Here we must see the physical interpretation of this. That is, if a particle is represented by a single harmonic wave, it extends in space and it has a definite momentum, and the position of the particle cannot be defined exactly according to uncertainty principle. And if it is represented by a wave packet, its position is definitely given and the momentum cannot be defined definitely. That is a result of saying that Schrodinger's equation has a wave packet solution. There is an important theorem in quantum mechanics, the Rhine-Fest theorem. The average values of observables are known as expectation values, and they satisfy these equations. That is, d by dt of expectation value of x is equal to 1 by m into expectation value of p, and d by dt of expectation value of p is equal to minus expectation values of del v. These equations represent the motion of the wave packet as a whole, and they resemble Newton's equations. And when the size of the wave packet is so small, these equations would have been identical to Newton's equations. This theorem is known as Rhine-Fest. Stationary states. In the case of time-independent systems, such as systems moving in a time-independent potential, there exists a special category of solutions of wave equations which describe stationary states. Such systems are described by time-independent Schrodinger's equations minus h cross squared by 2m del squared u plus v of x into u is equal to e into u of x. In these states, the position probability density mod psi square at every point x in space remains independent of time. So also do the average or expectation values of all the dynamical variables. Thank you for watching this PowerPoint.